So now that we know the basics of polar coordinates, right? How to convert, how to graph a polar point, and how to convert back and forth between rectangular and polar points. What I'd like to be able to do is say, okay, how can I do this for equations, right? How can I take this polar equation and convert it to a rectangular equation? Well, first, I want to be clear about this. You can't always do it. Right? It isn't always going to be possible to go back and forth, and you'll really see why in the next lecture when we start talking about graphing polar equations. We're going to get some graphs that you simply could never do with the rectangular system. But sometimes we can. All right, and doing this is always going to be based on our formulas for converting individual points. All right, so first, here's what I'm going to do. I'm going to have to be a little creative here. I have a formula for r, but it's got that square root in it. And I really don't have a formula for the sine of theta. But look, let's do this, right? I know that r equals the square root of x squared plus y squared. And I know that y is equal to r sine of theta. Okay, so here's what I'm going to do. I'm going to take this equation, solve it for the sine of theta. Sine of theta equals y over r. Let's substitute that into here. This becomes r equals 6y over r. Okay, well that's nice. I mean, it got the theta part out of there at least. So let's see. Let's simplify this a little bit. Let's multiply both sides by r. R squared equals 6y. Okay, well, good. Good, that's progress. Come back up here to my formula for r. If you square both sides of this, r squared equals x squared plus y squared. All right, excellent. Put that in here. X squared plus y squared equals 6y. Good, now let's clean this up just a little bit. Right, let's move the 6y over. X squared plus y squared minus 6y. Leave a little space here. I'm going to do something to this in a second. Equals 0. And we know what that is. Hopefully you remember what that is. Right? In rectangular coordinates, that's the equation of a circle. Okay, so here's the thing. Here's the thing to keep in mind. The shapes are the same. The set of points represented by these two different equations are the same. We're just describing them differently. Right? So if my rectangular version is a circle, then the polar version is a circle as well. Okay, so let's take this a little further. Let's see what's I want to find the center and the radius of this thing. So you remember how we do that. I'm going to complete the square here. So I'm going to add 9 and add 9. And this becomes x squared plus y minus 3 squared equals 3 squared. So this is a circle whose center is at 0, 3, and that's the center, and whose radius is 3. In other words, this is a circle, right? If I sketch the graph here, the center, oh, that wasn't very nice. Sorry, let me try to do a little better. The center is at over 0, up 3, and the radius is 3, so it's going to just be tangent to the x-axis. Right? So this equation, r equals 6 sine theta, is the polar form of the equation of a circle tangent to the x-axis. Okay, let's try another one. Let's try this thing. X squared plus y squared equals 6. Remember what we had on the last slide there, we had r squared equals x squared plus y squared. Well, good. I got x squared plus y squared here. Put r squared in there. R squared equals 6. So r is equal to the square root of 6. Okay, great. What do these circles represent? Well, this one is a circle whose center is at the origin and whose radius is, right, would be r squared. So the radius is the square root of 6. Two very different ways we've seen now, right? Two very different ways of representing the equation of a circle. One is that 6 sine theta. One is just r equals a number. Okay, so we're kind of starting to see more I don't want to necessarily say properties, but more attributes of these polar coordinates. One object, but two very different ways of representing it. Okay, so how about one more? This one is a little interesting. You can try this one, right? See what you come up with, right? Then we'll go ahead and do it together. So I'm going to use my formulas here, right? I know that x is equal to r cosine theta, and y is equal to r sine theta, and that equals 2. Okay, well, let's see. Maybe what can we do here? Let's factor the r out. R cosine theta plus sine theta equals 2, and then let's divide by r. Excuse me, divide by the cosine theta plus sine theta part. R is equal to 2 divided by cosine theta plus sine theta. That's a little on the messy side. Because you know what this is, right? The original equation up here, my rectangular equation, that's the equation of a line, right? Straight line. The equivalent is I'm going to go out there and say it's a messier version, right? It's not nearly as elegant, if you will. So these polar coordinates, polar equations, sometimes they're really helpful, and you'll see this really in the next section where we start talking about the graphs of polar equations. We're going to get some really very interesting graphs that we could really just never get with our rectangular coordinate systems. But it's not like a perfect replacement. Some things will be easier to do with our polar version of these numbers. Sometimes the rectangular version is going to be easier. Okay, so what's next? I've said it several times now, right? What's next? We're going to look at the graphs of polar equations. We're going to start out with some that are familiar, lines, circles, that kind of thing. Then from there, we're going to kind of move forward into some really much more interesting curves.